Thank you everyone for showing up on Monday just before lunch. This will be we're just going to go over some couple housekeeping things while some people are still joining. So this is going to be the first of 4 workshops. Today is going to be just a general broad overview of investment casting and using additive manufacturing for investment casting. Let's see, we're going to talk a little bit about some of the materials that are available and being used currently. The next couple of weeks, we're going to get week 2. We're going to talk more about fused filament fabrication and using SLA and DLP for investment casting. Week after that, we're going to go into wax and PMMA patterns. And then finally, the last workshop, we're going to be doing some just general design tips, things like that. Today will probably be the most PowerPoint heavy presentation. The rest are going to be week 2, week 3 will be about 50% PowerPoint and the other 50% demo. And the 4th one, we're doing some design stuff, is probably going to be almost entirely demos. Feel free to ask any questions at any time. I'll check the chat box intermittently. It'll be good if you ask me questions. Otherwise, I can start talking pretty fast, and then we'll be out of here in 20 minutes instead of the whole planned hour. So yeah, feel free to drop any questions. Wednesday, there's another workshop as well that we're running at UNI that Sam's running. It's going to be on robotics and offline programming. So if you're interested in that, or anyone else you know is interested in that, feel free to hop into that. And then last bit of housekeeping, finally, there's going to be a survey at the end of this, and there'll be one at the end of each session. Please fill that out. Let me know what more you want to learn about. I have these presentations made already, but if there's something more you want me to dive into, I can almost certainly add it somewhere in there. So without further ado, let's get started on the actual content. So looking at the guest list here, there's a lot of recognizable names or people that I've met before. Some of you work at investment casting foundries, others of you do not. So we're just going to give a quick rundown of the process just to make sure everyone's on the same page, especially for those not working in an IC foundry. So the general process has been the same for a while. We use a wax injection pattern to make our wax pattern that we're going to be used for casting. We'll take those and assemble on a tree. Depends on how big the casting is, how many you're putting on the tree. That varies based on your project. After we have our wax tree assembled, we'll build our shell on that by dipping it in different slurries to build up a shell that we can use later to stick into our autoclaving or burnout furnace to melt all that wax out. Afterwards, after all the wax is burnt out, we'll let the shell dry. We'll take it to our preheating furnace. We'll get it up to temp for our metal pouring. Pour whatever metal you're pouring in, let that cool. Afterwards, we'll knock off all the ceramic. And after that, we'll cut off our castings, and then they go off to post-processing. So pretty general work. Not much more on that. Let's talk about the actual additive manufacturing bit now. So the first 3D printers began appearing in the early 80s. There was some work done before, even as early as the 1950s, on some different model disposition or model center or metal sintering, things like that. But we didn't really start getting these 3D printers until the early 1980s. The first ones were similar to our SLA printers that were SLA and DLP printers that we're using currently. And there's really 4 facets of additive manufacturing that we're using to generate our additive or our investment casting patterns. Fused filament fabrication, which is kind of what everyone thinks about when they think about 3D printing. Extruded plastic layer by layer to develop shapes. Next up, we have a stereolithography. That's going to be typically involving a ultraviolet laser in a vat of photoreactive resin. So we'll start on the first layer, and the UV laser will cure our first layer of resin to our desired shape, go down a little bit, and then cure the next layer and build on top of each other until we have our developed pattern. Digital light process is very similar to the SLA process, but instead of using a UV layer, there's usually like a light projector that's curing each layer individually. And finally, binder jetting, We're going to see this mostly with PMMA patterns, where we're going to lay down a layer of sand, or in this case PMMA, which is polymethyl methacrylate, and then we're going to hit it with a resin to cure each layer and build on top of that for our patterns. Like I said before, we're going to go more into the weeds on these particular types of printing in the next couple of weeks, but a quick rundown of them right now. So wax printed patterns. This is a lot of people like using this, especially in the jewelry industry, where the printers aren't as large as, say, like a PMMA printer is. And it also matches your practices currently. So this material is very autoclavable. It's very similar to your pattern wax that you're already using. You can use your same methodologies to develop these patterns. You don't have to worry about removing parts from a tool, for instance, which helps with a lot of complex shapes. Big issue with this, though, the patterns can't be very large. The material itself is quite brittle. When you take this out of the printer, there's a white support wax on it that you can see on this picture on the bottom middle here. That's just to support overhangs when it's printing. That stuff has to be broken away and removed. We'll remove that by putting in a slightly heated IPA bath to melt that away, and then hopefully remove the rest. We use a lot of like clay tools to remove that stuff. That works pretty well. Another issue with these printers, they can be a little pricey. I've been looking into some newer ones. There are some smaller printers that are being developed right now that can do the same thing without the high price of purchasing one of these printers right now. They're more like their traditional 3D filament printers, but I haven't had a chance to use one yet, but they're currently being worked on at least. PMA printed patterns. This is the one we probably use the most here, for a couple reasons. One, because we can print larger patterns, and also the larger build volume of this printer allows to print a lot of even small things in large quantities. So we get a lot of use out of this printer. They're, unlike the wax patterns, they're pretty sturdy after printing. And even more so after dipping them in a red wax bath. After these are printed, they come out looking white, and it's a very porous material. So by dipping it in a red wax bath, that it seals up the pattern so that no moisture can seep in, and it gives it a little bit of rigidity as well. It also helps with shrinkage. As these patterns sit out undipped, they begin to shrink over time. You can see that in this graph over here that we did a little study on. Orange being cured for 10 minutes and dipping into a red wax bath, so you can see it shrunk a lot early on and then tapered off right away. The green pattern is a pattern we left out in room temperature over a week's worth of time. You can see it start to shrinking, kind of it leveled off right where the wax dipped finished. And then finally we left pattern in at an elevated curing temperature oven, and it continued to shrink for a while. So wax dipping that seal is going to maintain your geometric tolerances, and that's super helpful and also gives it a good bit of strength. Some cons to this printer: large investment up front. It's a full-sized monster. Our bill box on this is, I think it's about 1200 millimeters by 700 millimeters by 500, something similar to that. So we can fit a lot of patterns in here at once, but very expensive, especially the material is also quite expensive. And also this material has probably the steepest learning curve of all the printers that we're going to be talking about this next couple of weeks. Resin printed patterns. These are going to be your SLA and your DLP printer printed patterns. More recently, we've been doing a lot of research with a lot of resin companies on on different types of resins. A lot of the resins not made for investment casting tend to include a lot of ash in them after burnout. Obviously, that's not desirable for us. So we've been trying to find a structure that gives us enough strength to survive the post-processing section of the printing, but still, when we burn it out, there's not enough material to leave any measurable ash behind. Options for this printer, once again, this is another expanding market, so there are more and more printers are being made. Formlabs is developing some materials to use, and they're significantly cheaper than a large printer, like a large SLA printer, with similar ash content qualities and burnout qualities and strengths. The big pain point on these, the resins tend to be quite pricey, but they are beginning to drop with new resins being developed. Some printers can have surface quality issues, a lot of layering. We'll talk about more of that next week, but especially the DLP printers can have a lot of visible layers on the print. And finally, interior structure matters. And that's going to be a common theme in both resin printed patterns and SLA and FFF printed patterns. You can see in this picture in the middle, there's a honeycomb shape on the interior of the part. We use a couple different interior structures here. Tetrashell is a common one for non 3D systems printers. 3D system printers are going to use in their quick cast and quick cast diamond interior structures, and those work quite well. With fused filament, though, you often have to pick your own. There's not really a designated interior structure for any of this, so usually a little bit of upfront research is required on that. There we go. Finally, the last material that we're going to be using quite often is FFF. This is going to be your lowest investment to get into AM production. And often nowadays, there's going to be high schoolers in your area that have one of these on their desk at home. These are very widely adopted now. They're pretty simple to use. That being said, this is going to be the largest range in quality of your prints. If you buy a $150 printer, it very well may look like a $150 printed pattern. There's ways around it, but some printers just work better than others. Layer lines tend to be more visible in fused filament patterns, like the one on the right there. You can definitely see the large layer lines on here. And they're going to show up in your casting as well. Interior structures I talked about before, but they're going to affect how strong our pattern is, how much ash is going to be remaining. And the biggest downside, I think, is there's so many materials on the market, and a lot of them aren't going to be testing for their ash content. There is some pattern material available that's made specifically for investment casting. That's what we tend to use here when we're doing fused filament patterns for investment casting. So I often get asked, where's the best place to start for using AM for investment casting? And it's usually right here, the fused filament printer. There's printers on Amazon for $175. You can get a spool of the polycast. That's that filament used specifically for investment casting for another $50. So for $225, you can start making your prototype patterns today. Well, it's Amazon, so it's 3-day shipping, my bad. But yeah, you can get started soon. And finally, some things that you'll probably need at least to be a little bit familiar with in the next coming weeks. So some of the designing software and slicing software for our patterns. For design here, we usually use SolidWorks for most of our stuff. And we use also Rhinoceros for modeling our patterns. But there's a lot of free options on the market: FreeCAD, Blender, OpenSCAD, things like that. These are all free and open source. But if whatever you're using should be okay. As long as you can save your model as an STL, you'll be good to go. Slicing, this is going to be different for maybe every printer. You can make, like on the ones listed here, Kira, that can work with almost every FFF printer. But things like SLA and DLP, they're going to have their own custom software for setting up prints. PMMA, same thing. There's its own custom software to start prints with that. Those are always provided with the printers usually. So those will come up as necessary if you're making an investment on one of those printers. So that's really it for the PowerPoint section. We're going to get going on some demos here, just run through some things. Does anyone have any questions before we switch over, though? I'm sure you can unmute, but you can still type in the chat box if necessary. Let this sit there while I get everything else pulled up. Sorry about that. Switch screens real quick. All right, hopefully everyone sees SolidWorks now. We're looking at a pattern that we print here quite often. This is our standard investment casting tree. Unlike a lot of production facilities, we're using almost entirely 3D printed patterns for our trees. We like to change them a lot, add different features. You can see in here, there's a little spot for some moisture sensors to measure the moisture of the shells as we dip them so we can more accurately predict when they're dry. A sprue hole for attachment to the robotic cell. And we add a lot of things like this often. So it's pretty conducive for us to make a lot of different pattern trees and print them. But what I wanted to talk about today for printing in any printer, you're going to need an STL to actually print. So when I save in SolidWorks, for example, the save menu here, we go to STL, and this is going to vary from software to software, but there's usually some way to alter how well your STLs are produced. So once we open up this options screen on the STL menu, we're going to look at this resolution. If you ever seen a 3D printed part have a lot of blocks in it, that's almost certainly because these weren't adjusted. So if I turn my deviation all the way down here and the angle all the way down, you can see that the circles here are going to actually print as straight lines rather than circles. Obviously not desirable. I'm going to save it out as screw bad STL, just to give a comparison in the 3D printing software. And then we're going to save another one with the resolution turned all the way up. On the angle, we usually actually for SolidWorks, we stop at 5 degrees. You can increase the resolution of the angle even more, but there's some diminishing returns on how circular this is, and by increasing this even more, the STL file size will continue to grow and grow and grow. And on some patterns, it can grow too much to where often, like if you drop it in your slicing software, it'll crash the slicing software because of being too large a size. So we found this 5-degree angle for STLs actually works really well on SolidWorks. I know if you're using Rhino, you don't actually have the same settings. It asks you how many triangles you want to make on your STL. And I don't have a good number for that yet. I usually try to keep my file size under a certain number rather than trying to like find a good range because it's going to change from pattern to pattern. So I'll save this out. And if it also does a preview on SolidWorks, so you can see how many triangles it's using to make these shapes. So we're going to take those two patterns and we're going to open up Cura, which is we use the slicing software for pretty much all of our FFF patterns. And then sometimes we use it to alter different geometries to fit into the other printers as well. Let's make sure I'm sharing the correct screen. All right, so we opened up Ultimaker Cura here. I'm going to give you a quick rundown of this software in case you've never used it before. So if you go to this printer tab here and add printer, it'll go to a list of available printers that you can use. Ultimaker is the kind of default. I believe they own this software, but there's a whole list of different softwares here that you can, or different printers that are have custom settings that are already integrated into Cura. So let's just use MakerBot is actually I'm going to be doing a really large pattern. We'll start with MakerBot just for get started here. So when I select that printer, there's going to be some different settings that are going to pop up in these menus. So in this case, we're going to be running a filament. If polycast isn't on here, there's usually the ability to make custom materials. They have Polymax, but not Polycast. We'll use Polymax as it's somewhat similar to Polycast for now. And then we're going to go into our main settings tab here. So some important things to change. We want our pattern to be able to survive post-processing, and we want it to be able to survive the dipping process, but we need to have our material low enough to where we burn it out and it doesn't produce as much ash. So some settings we can do to change this, we can change layer height. That's what this first one is. This is mostly going to affect surface finish. So if I do extra fine, the layers are only going to be 0.06 millimeters tall. It'll take a really long time to print, but the surface finish will look pretty good on it. Alternatively, if it's like a really early prototype and you're not necessarily too worried about the surface finish of it yet, we can do something like extra coarse and it's going to print it really, really fast. So let's start there. Walls, we typically do 2 walls. So this is going to be the solid layers on the outside of the pattern. This is largely going to be picked by the nozzle size of the FFF printer. But if you're running a 0.8 millimeter nozzle and you want the wall thickness to be 0.8, you're only going to do 1 wall line count here. But if it's 0.4, you're going to do 2, so on and so forth. So in this case, it's going to make the wall of our pattern 2 lines thick at 0.4 millimeter gaps, basically, and it'll overlap any that it needs to. This is going to be the same for top and bottom. There's going to be a solid layer on the top and bottom. You can pick how many layers are completely solid. 2 is pretty standard and works pretty well. And the most important one here is infill. So let's drop that STL I made earlier into here. Hope it fits. Oh no, I got to pick a bigger printer. So let's make one real quick. Custom FF printers, machine settings, we'll make it 1,000 millimeters cubed, just for demonstration. So that fits in here. So when I run the slicer here, we can look at the preview. Oh, it's really slow. So here's our infill structure that we picked. I believe this was just a simple cross pattern at 10%. There's a lot of infill going on here. It's likely that if we were to burn something out like this, there'd be a lot of ash involved. So if we go back, we were running a 20% infill percent. We can half that, rerun our slicer. You can see it's not as dense anymore. Now, the only issue with this is maybe the skin of the pattern now. It might be too thin to actually survive any post-processing or any dipping sequence. Now, luckily for us, we don't actually print our trees with PLA, but a lot oftentimes patterns will be. And when the pattern is small enough, the ash content can be pretty marginal in the first place. So sometimes you can get away with it. Also, infill patterns, typically where you're going to be either using grid or cross. We haven't done much experiment with the different infills with PLA yet. But there's definitely some interesting ones that could be beneficial to the investment casting process. So the other one, often if we're printing something just like a standard tool for sand casting, for instance, we might use a triangle to give it a lot of strength. But in our case, strength isn't necessarily a good thing at a certain point, right? Because once we're burning this out, we want the material to fail and collapse on itself so it doesn't crack our shell as it's expanding and burning out, right? What else to talk? Those are really the only settings that really affect how a pattern or tree might be affected in terms of casting wise. The rest of the settings are based on like how well the surface finish is going to come out or how fast it's printed. You might have to adjust some different settings depending on the material and things like that you're using. Any questions so far? I know I'm dumping a lot of information, but it's going to get used in the next coming weeks. So
How do you make your trees if you don't print them?
our investment casting trees, so we pretty much exclusively use PMMA printed trees. We've talked about getting like an injection tool for it, but a lot of times we change our trees pretty often to incorporate different sensors and things like that. So we'd have to do a lot of tool modifications along the way. And frankly, we don't really print for production. Most of our prints are for research, so we're not using nearly as many trees as a typical working foundry would. Any other questions before I swap to some more Ultimaker Cura settings? All right. So let's say you bought a printer that's not on the list of printers on the predetermined list, right? So we'll just pick a custom tree here, or a custom printer, sorry. Add it. And then it's going to give our list of settings. Usually the manufacturer will be pretty good at providing all these settings, especially with depth and height. Build plate's pretty self-explanatory. Most of them are rectangle. Do you have a heated bed or not? I think a lot of origins are at the bottom left corner, not the center. Things like that. Now, this is kind of where it gets tricky. Luckily, the internet's pretty helpful in this case, but the G-code flavor, there's this whole list of different stuff. That's going to have to be told to you by either the manufacturer or just someone helpful online. And then the start G-code, they're pretty similar between printers now, but some of them have some gimmicks that you need to include in here. I, for one, like this one, I just had to do a home command on the printer to get it to go to its starting origin on startup. The other thing is if you have more than one extruder, you might need to add a second one here. So there's two different types of extruders. You might be running different nozzle sizes, different materials in all of those. There's some materials that rather than having to remove them mechanically with some like snips or something like that. It's called PBA. You can dissolve it in water, so you can throw your pattern in water and let those supports dissolve away. Other than that, you're selecting filament type, diameter, nozzle size, if there's an offset. There's a couple of our printers that were not running on the software that we're now running on this because frankly it slices better than the slicer that the printers came with from a decade ago at this point. So it's been a pretty simple change. And this whole slicing software is free, which is great for us at the university. We don't have to go through the whole headache of shopping looking for different slicing softwares. Okay. Well, I did the thing where I talked too fast because I got on a roll. There's a few more things to cover, but does anyone have any questions in general about investment casting, additive manufacturing, anything like that? All right. Then I have to pull something up on SolidWorks here. Just give me a few minutes here. Sorry about this. I'm working on a laptop that just updated to Windows 11, so all my stuff is all over the place right now. So I can't get this fixed. Okay. Okay. So those STLs I saved out earlier, we're gonna do a little side-by-side comparison here. Where's the other one at? Not you. Not you. So same model saved out with different STLs. The most blatant example of why adjusting those settings really matters here is on the insert for the all threaded rod that we attach. You can see how blocky and squared off the circle is. This is going to use more triangles to give a nice, about as close to a circle as you can get. It's really hard for software to generate circles in different programs. If you ever really looked at something up close, even on like AutoCAD, it's not really a circle. It's just a bunch of really tiny straight lines doing the best it can to develop a circle. And the other thing I was trying to pull up was another model that I was gonna kind of walk through, but I'm off campus right now and I can't seem to get it to download from Google Drive. So that kind of put a damper on that. Oh, sorry. What film? Hold on, I got a question from AJ. I apologize, I had to step away for another meeting. However, what filaments do you recommend for processing through the investment casting operation? Maybe you'll cover this in another talk, so disregard. So now I talked about it a little bit after the FFF pattern discussion. So there is if we're using FFF patterns, we're using pretty much exclusively polycast because it was developed to be used in investment casting. So it's going to have a lower ash content. We haven't done any expansion tests on it yet. And I'm going to kind of add it to my list now because whenever we test a new material for investment casting, that's one of the things we baseline to see how much it's expanding when it's heating up to see if it's going to crack our shell. There's been a few pattern materials that we looked at that were like really, really good ash content, but when we started to heat them up, would expand way more than a lot of our other materials would. And lo and behold, they ended up cracking shells just because it wasn't collapsing soon enough and is expanding way too much for the shell to handle. So either dip it more times or significantly more times and hope for the best, or disregard it entirely. So PowerPoint wise and demo wise, I kind of since I can't access the W drive, I need to download some more things. I'll kind of push those into the next presentation. But right now we can just do a question and answer session. I can help with any projects you're working on, anything additive manufacturing or investment casting related. So we'll leave it there, and I'll take any questions you guys have. See, this is what I get for scheduling this on a Monday. Everyone's tired and not awake yet. It was planned, I swear. Switch this. And also, I'll just leave this up as people are hopping off or typing up questions. If you need to contact me with any questions you have, I have my email there listed. Happy to help. Does the quality of the print vary more based on the brand of printer or the price? I'd say honestly, it's often the price. Usually the more expensive printers will give you more control of how the printer is actually printing. You can refine the qualities of it a little better. I not really brand specific to say. I for fuse filament especially, I'm not sure if there's like one crowning jewel printer or if they're all run pretty much the same set of G code. It's really going to differ on the extruder part and the nozzle part. And even then, a lot of the nozzles and extruders are becoming more and more homogenized, and they're all using very similar brands on that end of things. I-beam blue wax filament. I have not. Do you know if that is that used mostly in like FFF printers? All right. Well, we haven't before, um, but we most certainly will be now. I'm really interested now. In like the surface finish and shell adherence. Hey AJ, did you dip it in a like a wash before you printed with it too? Just like your typical wax wash? Oh, okay. The wax printer patterns we use as well. You guys use Citru Etch. The 3D printed wax patterns, we haven't needed to etch them first. But we're usually printing pretty small things on that printer. And it usually doesn't have much issue sticking because when you clean off the parts, in that IPA, it kind of roughs up the surface a little bit already. So it wasn't as much of a problem for the slurry to attach. Interesting. No, we'll definitely give it a shot. Are there any dimensional differences when using certain printers and materials? So the dimensional differences can change, especially if since you're heating up the filament, it's expanding during that time, right? So as it starts to cool, it's going to begin shrinking again. A lot of materials already have that scale factor baked in to their materials. For all of our printers, we include some sort of shrink factor. And it's usually almost entirely material specific. So we'll just print like a 1-inch cube and measure it after to see how much we're shrinking based on the material, and then add a scaling factor to that afterwards. Printer wise, I usually the printers are pretty decent unless there's like some really bad axis problems on the printer. If it's like overshooting too much, you'll see that more in the cheaper printers than the more expensive ones. But if it's a consistent theme, regardless of material, it might be the printer itself and trouble with the axes. Sorry. Yeah, thanks for the lead on the I-beam blue wax filament. We'll give it a shot and see how it turns out for us. But any other questions? If not, we'll wrap things up. Get you guys to an early lunch. Oh, yeah. Thanks for everyone for coming in. Next week we'll be doing a lot more demos than PowerPoints. So sorry if you hate PowerPoints and everything. So have a good rest of your day, everyone.